Professor Shankar Prakriya, mobile broadband service support over cognitive radio networks. This session would be chaired by Professor Sunil Kumar.
I am Shankar from IIT Delhi. We have, this is a team consisting, we have 4 teams in this project. One from IIT Delhi, myself, Pradesh Dev. Then we have Institute of Radio Physics and Electronics from Calcutta, LMIT, Information Technology from JP. And there is So this is the broad outline of our theme. So we have 4 institutes, PIs and OPIs from each of the institutes, good number of PhD students. In fact, there are 17 PhD students in this project. We have 17 PhD students in this project. And also we have been having collaborations with other institutes. The central goal of the project is to deal with various problems related to signal processing, physical air communication, networks, etc. All the problems related to cognitive radio. Because cognitive radio requires solution to a large number of problems related to these areas. And a good understanding of all these areas is required. This is why we are teamed up with these institutes are teamed up. We have been along with them different kinds of specializations. NILIST has specialization in security. We have specialization in IIT Delhi in physical air communications and networks, LMIT in signal processing, and IRP in implementing systems, just threads. So we have made good progress in curriculum development, etc. So Swadesh, would like to discuss. We were advised by our mentors to focus on one application and keep it in mind when we work on various problems. So I think Swadesh. So as we progressed in our project, we were advised to have a common theme of research. So objective was we picked up has been rural broadband access. This is kind of a crude architecture. So we go through a few slides. So basically the work involves multiple layers. So we individually worked on network layer, MAC layer, and security and so on, and then also we have combined different layers in terms of systems appropriately. So specifically the network systems MAC have been dealt with by Delhi team, hardware testbed radio physics and LMIT security has been handled by this nearest team in Arunachal Pradesh, and so that is how. So initial part of the work we focused on the purely MAC aspect. Basically, what is the if let's say there are multiple cognitive radio channels, we wanted to study under what condition single radio channel access is beneficial compared to switching around multiple radio channels. We considered the different objectives. Let's say if the objective is energy efficiency, like cognitive radio sensor network, then what is the rate of what is the dynamics of the channel, under which condition we should choose for single radio design or switched we call single channel access versus switch multi-channel access. So we'll just go through very briefly. So and then once we figured out that under certain channel dynamic condition, this single channel access is better approach than other, and then we further looked into the fine tuning. If we indeed go for single radio access based approach, single channel we call SCDSS, single channel dynamic spectrum access. So then we fine tune what should be my intersensing period, what should be my cognitive the packet size, secondary packet size, so that the optimum performance can be achieved. without hurting the primary performance. I'll skip through very quickly. So now, that aspect of the problem were purely focusing on the cognitive radio, meaning that the secondary node is only capable of accessing cognitive channel. Now, when we are interested in the quality of service support, so we consider the scenario where the device has access to the license band as well as cognitive band. Now so how do we provide this cost-effective service to the users? So we call cognitive multi-homing. So this basic multi-homing concept, actually this multi-homing concept has evolved from our previous cellular network one. And then what we have considered here in addition is the cognitive part actually. So the idea is that, if a specific quality of service application is given, then this approach decides what fraction of the cognitive channel and what fraction of the secondary LT channel should be used. So in these prior studies, we considered for analytic modeling the channel availability is modeled as on-off process. So on duration is exponential duration with some let's say average lambda, and off duration is also exponentially distributed for average mu and so on. That is for analytical tractability. So we further wanted to investigate the actual channel availability. So for that we considered these the 802.11 channel. So cognitive 802.11 was our objective. So we actually captured these packets and then started what is the packet arrival process. And what we came up with is that we came up with a Gaussian mixture model, and then we showed that this is coming to be a much better fit. So this result is kind of we consider in a control environment as well as in general environment, like in IIT Delhi, in the wind tunnel where there are multiple access, the white space communication, Wi-Fi communication is going on. Under that condition, what is the characteristics? And also we consider a scenario where there is a controlled Wi-Fi access point, and we started the internet access. But in both cases, the GA model works well. That's what we shown. Of course, the parameters are going to be different on these two scenarios. So further on, so focusing towards rural broadband, what we have been working, this some progress we have made and we have explained, is that considering that the household devices, like each household is assumed to have Wi-Fi access point, and then we are considering these household Wi-Fi access points.
Can you please maintain silence? We can hear the noise on that. It's a very interesting topic, so this is discussing. Thank you.
So the idea of what we wanted to do is that in rural broadband, the challenge that we perceive is that the service provider is not interested in deploying these base stations because that is not cost effective for them. So we are considering there is the national NOFM scheme, meaning that is up to Panchayat base station there will be optical fiber connectivity. And we are also considering that at that point there will be a base station that is also, let's say, installed by the government. And then from that point on, in the deep rural villages there is no other tower installed. So we want to we are proposing that each household access points can collaboratively transmit in terms of uplink transmission, and downlink transmission is not a constraint because base station can have high power actually. So here the main challenge that we have is the distributed beamforming, and this is what we have been currently working, and we have had some basic proof of concept, hardware based proof of concept. So what we have shown here is that the leftmost node is the main transmitter, we call, let's say, primary transmitter, and then the intermediate node which is trying to collaboratively beamform with respect to for the reception at the rightmost node actually. So the leftmost node is the kind of main node, and then other node is trying to control. So we have shown that by controlling this phase properly, we can gain significantly in terms of the time saving and energy saving. So I very briefly wanted to indicate that. So this objective has been, actually we have two purposes. One is for rural broadband, and also we are looking for multi-hub energy transfer. So RF energy transfer. So this result that we are showing here, because that was easy to capture for us for the demonstration purpose. So this is like if these two nodes want to transmit at the same frequency and phase, there will be some phase asynchronism because two devices have their independent clocks. So if they are not trying to synchronize with each other, phase and frequency synchronization, then the performance is something. And if their phase and frequency synchronized, then we see that for 50 seconds of charging, we can gain 12% saving in terms of, it's not readable, in terms of time gain. And correspondingly, if I want to raise the capacitor's voltage level, which is the storage device's voltage level, up to 250 millivolt, 36% of voltage gain is achievable. And likewise, if we charge for higher time, corresponding. So we are currently fine-tuning this for further demonstration of the cognitive broadband transmission. So this is what is the state with respect to the systems approach that we have been working, and Shankar will carry forward. Okay. So there is some work related to physical layer to study coexisting underlay networks. So in the past, people have studied coexisting underlay networks and as an optimization problem. So you run an algorithm and give you how to control the networks and so on. Instead, what I've done is to take two secondary networks and operate it along with the primary and try to clearly indicate what the trade-offs are and how to control the networks and so on. So this has applications, for example, in LTE, the release 10, etc. We have relay stations. We can have the base station and the relay station communicating simultaneously. Of course, that is standard in underlay framework. But what I'm saying is that we can have two of these relay stations transmit simultaneously to the respective users registered with them, while the base station transmits to its own user. Basically, they are all part of the same network, although we're calling them primary and secondary. So in such a case, how do you do the network management? What should be the network management tool? When should you operate both the networks? When should you operate only one network? What happens if you, obviously when both the networks are operational, the secondary sources S1 and S2 are both going to transmit, they're going to cause interference to the primary receiver. That interference has to be carefully controlled. So while you're keeping that interference threshold the same, should you operate both? Should you operate only one? This is the question. And we answered that in an analytically proper fashion. We showed that if the target rates of the secondary users are small, then we should operate both, or we should operate only one. And if you're operating both, we tell you precisely how much interference threshold, how it should be shared between the two secondary nodes. So we did this also for fixed rate signaling and for the more interesting adaptive rate signaling, when it's adopted in both the secondary networks. So we give proper network management tools. And we do the same sort of things also for security point of view. Now, what we find is that it is advantageous for the primary to have two secondary networks operating. And with what power they transmit, they can also choose it to maximize their own rate or throughput. But there may be a different optimization for security point of view, the primary security. From the point of view of the primary, if there are two secondary transmitters transmitting, it is beneficial because it can give more physical layer secrecy. So we studied all the security aspects from the point of view of the primary and also from the point of view of the secondary. So this work is of two parts, one relating to the network management tools and cognitive radio part, and the second part which is physical. So we submitted these works to various, and also trying to find for a patent for this component of it, for the network management tools, because these are of very great practical significance. And we've also done work related to secrecy of two-hop cognitive relay networks. It has been published in communication letters. And we've also done work on secrecy performance when there are jammers, which has also been published in Anti-Fake Transactions on web technology. We did work on buffer relaying. So this buffer relaying basically means that picking up packets from the source, storing it in the relay and then forwarding it to the destination. Why do things change here? The things change here because we have cognitive radio. We are trying to keep the interference to the primary receiver a constant, which means that the power that is used by the secondary source and the secondary relay are random variables, which means that the SNRs are off, both the hops are varying widely. So how we manage such a situation? We show that adaptive link selection is the way to do. That means you choose whichever link is better, is beneficial. Now that will affect the many things. It will affect youth throughput, it will affect SCR, it will affect delay. So what I try to show is that we study the trade-offs between these three things and analytically show. Derive expressions for all of these and show the trade-offs. It is part of it is appearing put also in archive. We also involved a new buffer mechanism that allows you to trade off throughput for better SCR. So that has been applying for patent for this. And also studied the multiple constellation sizes. And because of the fact that SNRs are varying very widely, it's also beneficial to have multiple constellation sizes. Sometimes you want to use BPSK, sometimes UPSK, sometimes 16 QAM and so on. We also studied the multi-hop relay networks from the same spirit, and we try to show with our various algorithms that are peculiar to cognitive radio and analyze their performance. Because of the fact that SNRs are varying a lot, to maintain some quality of service, all the relay clusters have to be close to each other, which also means that skipping the hops can be very beneficial in cognitive radio, much more than in cooperative networks. So what we show is that if you allow the relay nodes to transmit directly to the destination and then stop your transmission at that particular point, you have much higher gains in throughput. Of course, it can be done for cooperative networks. What we show is that for cognitive radio networks, these gains can be tremendous because of operating underlay mode. So these are in various. We also studied this hybrid interview underlay networks, taking into account the primary traffic. This work is to be submitted. A significant part of our effort was also in energy harvesting. It's important in the context of 5G, how IoT devices being used and so on. Or sensor networks, many of these applications are required. So we have proposed a joint energy and spectrum sharing protocol, and it was that should be PMRC 2014, and it was also published in IEEE Transactions of Nuclear Technology in 2017. We show that it is advantageous for the primary to share its excessive power to the secondary, so that the secondary can. So then we suggested that the energy harvesting nodes can also have a small battery, and we show how batteries can be managed efficiently and intelligently. And this has been published in IEEE Systems Journal, and the patent application also has been filed. We want to do this a few battery management techniques. We also studied the basic two-hop underlay networks and something that's counterintuitive. We show that relays are only useful in this energy when they are energy harvesting relays. So it's only useful when they have multiple antennas. Otherwise, it's not very useful because of the fact that very little energy is actually harvested. So we published it in conferences and journals. Yep.
Very quickly, I will try to highlight some of the topics that on which we have worked for last 3 years. That advanced renowned energy detection-based spectrum sensing, the generalized rating channel. We have done work on detailed simulation study for capacity analysis for TV white spaces, spectrum occupancy measurements, modeling, and prediction for dynamic spectrum access also been done in the second year of the project. Interference mitigation in MMO-based CR systems, and we have also developed SDR-based computer experience. These are some of the highlight of our entire work that we have carried out in the last 3 years. And for last 6 months, our team was involved in the 3 topics that we have mentioned over here: the creation of radio environment map through breeding-based spatial interpolation, development of Android-based spectrum orthography dynamite, and we also have completed the first draft of the book that we have promised on fundamentals of cognitive radio, a practical perspective. So So these are the three major topics that we have highlighted for last. So these are the three major topics on which we are actually working for the last 6 months, and my student will be explaining the first two topics that we have noted over here.
Can you try to wrap up?
Yeah, exactly. So this was the work we started in January, and that is radio map through grading-based spatial interpolation. Actually, it is infeasible to go at each and every location and conduct the measurement surveys for spectrum occupancy measurements. So what we tried was that we envisaged to generate a spatio-temporal map of spectrum occupancy for dynamic spectrum access. Now, there are two steps for spatial and then temporal. So, step 1 has already been completed, where we have spatially interpolated the data at target points where I call the interpolated points through kriging-based interpolation from the data set at the measurement points, that where the measurement had physically taken. So this step has been already completed, and now the step 2 is in pipeline. So now we have, how did we check the accuracy of the interpolation? That is based on the mean absolute error in estimating the interpolated values with respect to different lags. And lag is between the control point and the interpolated point. Control point where the measurement was taken. So this is the measurement site at LNMIT. So red dots the major points where the measurements were taken, and blue the target interpolation points. So these are the preliminary results. That here, this is the three-dimensional at left hand side, three-dimensional plot where spectrum occupancy and x coordinate and y coordinates are there. So these are not particularly cones, but multiple values of spectrum occupancy at different locations. So here you can see the table in which I am showing the accuracy through mean absolute error. So as I am increasing the lag, means the distance between the interpolated point and the target point, so mean absolute error is getting increased. And a minimum we had achieved at 0.1 meter, that is 0.007. So the second one is LNMIT Spectrum Observatory.
So I'll be explaining LNMIT Spectrum Observatory. In the last meeting, we had demonstrated a spectrum observatory which was based on MATLAB, and it was for desktop PC version. And it was suggested that it should be implemented on Android. So we have done that, and we have incorporated databases from 6 or 7 different locations. And you can also export the data for further analysis or some other analysis. And the demo is available with us. So if anyone from the panel wants to see it, we can demonstrate it after the presentation, as we are running short of time.
So this is some of the highlights that we have done in the past 3 years, and we have already given details of all these works in the previous workshop. And basically we are concentrating on some of the works on experiment and some of the works based on theory. The first 3, which tells about the testbed setup, about the using USLPs, and then we take the spectrum of occupancy measurements in and around Kolkata, and then FPG implementation, improved spectrum sensing using genetic algorithm. And some of the theoretical works, we have done the resource allocations and cooperative communications for cognitive femtocells in heterogeneous network, and rate allocations in wireless backhaul for rural broadband using TV white space. And these are some of the works which we have done in the last 6 months are the experimental demonstration of wireless software-defined optical transmission in picocellular networks, which I will slightly explain in one of my slides. And another work which we have done, proactive catching with content-based pricing for cooperative femtocells, just to reduce the network load.
Yeah, 30 minutes total. So including
Very quickly, we just go through our works. So this I'm not going to, these are some of the laboratory setups which we have done using USLPs. I'm not going into details of all of this. And these are just significance, verifications, and relevance, and some of the problems which we are working with, some of the problems that GNU radio is really giving problems in controlling the user service, and we are trying to build up the Microsoft Visual C++ codes to control this user service. And the second work, which just is the cooperative spectrum access for femtocells using hybrid AR2 feedback, which is actually increase the throughput of the macrocells, which belongs to the femtocells, using the cooperative communications, and as well as the femto access, the femto users can increase the opportunity in their transmissions. And the third work, and these are significant, I'm just skipping all these things. And the third work which we have done is the software-defined optical transmissions. Here you see that in the first side, we have generated the RF signals all optically and transmitted to the optical fiber, and then we transmitted it wirelessly, and the USF is at the end as receiving. And we have shown that the very good bit error performance has been obtained, and this is very useful in picocellular network concepts. And these are all the significance. I'm not going to do this. And the last work which we have done is the proactive caching, just to reduce the network load. And as you see that if we can include a cache memory in the femto access point, and then if the network load demand doesn't change very fast, then we can show that the femtocell load is reduced drastically if we do proactive caching technique. I'm not going to go into details of all these things because of shortage of time.
So I'll keep it very short. In Nerist, we mainly worked on the security aspect of CRM. We did use a lot of techniques like clustering, data mining, game theory, not mentioned here, and we used some radio linking techniques also, like TDOA and angle of arrival and all these things. In the last 6 months, we worked mainly on using Markov chain and some other techniques, So this was a very short study done on the spectral occupancy in the Northeast India. This is still continuing in other parts of Northeast. So we are looking mainly at the spectral occupancy of Doordarshan, which is the only terrestrial operator in India, TV terrestrial operator. And apart from this, this is what we worked on using some threshold techniques and Markov chain, and as of now we are getting good results, and we're trying to implement all these in the testbed because this has been done in simulation. Thank you.
Coming to the curriculum part of it, as I already discussed, a book on fundamentals of cognitive radio has been completed. The copy of the book is with the panel of experts. Please have a look at it. So it will be really beneficial for both undergraduate as well as postgraduate. It's important because cognitive radio requires understanding of various aspects of signal processing, physical layer communications, and also a little bit of machine learning, network layer, a little bit of networks. So it needs a whole systems-based approach. Because of this, I think the book will be very useful as a teaching aid. For the same reason, an elective course on cognitive radio was also taught at LNMIT for 3 years. A new master's program was developed at LNMIT on communications with emphasis on systems levels approach based on what we have learned in this project, the deficiencies of our current curricula. Lab with experiments related to cognitive radio was also developed. And a new course on cognitive radio is being continued as a part of a course in IRPE. A new elective course again on cognitive radio networks was introduced at NEXT. This book, of course, we already read. Our outreach activity has been extensive. Of course, we could not list all of them here. We had lots of workshops, seminars, which we all got together with participation from faculty and students of many institutes. And we also had given a large number of lectures, invited lectures, seminars, tutorials at various places in India and abroad. One faculty from Punjab had done work at IIT Delhi on this IT area project and had a publication out of it. So it has benefited a larger community than what we had envisaged. Our outreach has been very, very successful. Part of summary of achievements, we had 70 research scholars, most of whom will be completing very, very soon, definitely within a year. and several MTech and BTech students also benefited because they were also used for various activities in this project. The project resulted in important research findings, new insights obtained in various aspects of cognitive review, because at the time, at least even today, our understanding of performance of cognitive review is not very particularly good, which is the reason why it has not been extensively deployed. So this research work was very, very important. It has resulted in a large number of journals and conference publications, 3 book chapters, 1 patent applications, and 2 others being filed. And of course, in curriculum, as I already discussed, we had very, very significant activity. And outreach also, we had significant contribution. And the spectrum occupancy measurements and testing that we carried out will be very useful. I think if you have, please have a look at the Android version of the spectrum observability that we covered.
So it's very obvious, it's a very, academically very sound work, and analytically also it's very sound work. There is a team involved. So, I think the initial project was more on the rural connectivity.
On the other hand, our project proposal did not mention rural connectivity.
Okay.
It only had work related to various aspects, and we thought that together we will be contributing in our own areas.
So
But we were encouraged by the mentors.
I'm curious on 2 aspects. Do we have TV white spaces in India? Have you migrated to all digital in India? We are talking of TV white space in US. We know that we don't have any analog transmission, so those TV bands are available by FCC for CRN.
Here it was never used. Users were not to respect channels. Actually,
That's
there are a lot of lots of unused TV channels are there. In US there is a lot of opportunities there, but
Yeah.
scope of using TV devices is more in India.
There are lots of bands that are still unused.
TV space is quite long.
Yeah, so basically you have a lot of.
Because those are unutilized, because it is wide, but otherwise those which is being utilized, that how it can be utilized for our secondary user communication purpose, that we are actually contemplating.
So cellular companies have been fighting to use it for other purposes like backhaul, etc.
Even those white spaces, which is totally white spaces, even they will not give us freely. Like even those protocols we have to maintain.
So my second question, partly because of the less familiarity with the Indian environment. In the Northeast, you are doing the spectrum measurement, but most of the time you are not using this, very little occupancy in the Northeast, right? So what is the significance of doing spectrum management for the Northeast, other than academic value?
Mainly the study was conducted to find out the occupancy, not just in Northeast. I mean, these people have done it in Rajasthan area, I think, and there are papers published for southern part of the India and even central India. So the idea was to complete the picture so that in future, if anything comes out from the government side, like the FCC in US, so we will be ready with the data to provide to them. That was the main idea.
So this, maybe I've done a lot of work with CRN, mainly for DoD in US, and we have published a lot of papers including a book. So we look into CRN mainly when there is spectrum congestion. CRN becomes useful because you can opportunistically try to use the spectrum. Do we have that scenario in India other than maybe some metros?
So we have actually looked at both aspects on dynamic spectrum access perspective as well as white space access perspective. So in first part of our work, we were focusing primarily on the dynamic spectrum access, where the spectrum is fairly dynamic. So how to utilize that is what was the objective. Dynamic means how frequently a primary is coming to occupy the band. So in this case, so when I am talking about dynamic spectrum access, we are talking about cellular band, Wi-Fi band, particularly. So now with respect to white space, possibly there is also dynamic term coming. So we, as Dr. Dasbarman mentioned, that there are two bands currently being used for digital TV transmission in India, at least in Delhi, what we have measured. Even the point that we are trying to see is that even in these two bands which are currently being used, we can possibly reuse that band if we transmit at certain power, depending on how far away we are from the TV transmission station. So possibly that is one interest that we need to measure the spectrum availability even in the occupied band. So I am, for example, there is a base station in Pitampura in Delhi, and then if I am measuring the signal strength at IIT Delhi, we are finding some strength, and possibly we have to optimize my secondary transmission accordingly. If we measure instead another 5 kilometers away, possibly my on the same overlapping band, my usage pattern will be different. So possibly multi-hopping versus direct transmission or power control, etc. So that is.
Within the same cellular network, you can have frequency reuse. Much of my work has been the finished thing that I
But
discussed.
that happens anyway.
Yeah.
So this reuse is very common in wireless networks.
But not within the same cell.
No, within the same cell.
Using dynamic spectrum access techniques. That is what we are.
So can I just want a quick clarification to what I said? So what you are suggesting is that somebody else's spectrum I can sort of steal and not steal, but
They are all part of the same network. I'm saying that
somebody
this
else's spectrum.
Yeah.
Is that what this is? The Airtel uses Vodafone's spectrum.
No,
That's not what you mean.
no, same band. I'm talking about the same band. Same cellular band. You are transmitting to your user. The same frequency is reused by the radio stations to communicate to the users registered with them. So you specific frequency reuse, but it is being done in a way.
The standard way they use.
But in the way in which it is being done is to ensure that the interference cost.
I take this off.
Yeah, we can do it offline.
This is more about advocacy and so on. So I understand Microsoft has faced some challenges with the government. Since you're in Delhi and so on, have you had any conversations with the TRAI or given your expertise in the area in terms of sharing the textual observations with them?
So we have not actually talked with TRAI. Currently, we are doing some experimental studies, and we are interested in once we have a fine-tuned observations, we would like to talk to this TRAI. Actually, we want to demonstrate how much overlapping is allowed at what primary receive power level, like that. So, for example, 5 megahertz band is the one channel TV channel. And we see that if the primary, the secondary is certain distance away, then entire overlap is okay without hurting the primary reception process. So we are trying to characterize the set of the system, and then we would like to. We have not currently discussed with TRAI with respect to that. Yes, yeah, we'll contact you. Thank you.
What is the extent to which the 3 or 4 institutions have actually worked in any of the research?
So one problem that we have, LNMIT and IIT Delhi have worked on is this spectrum characterization, that GM modeling. In fact, we both of us were interested in modeling. So we proposed, we shared the LNMIT's data were shared to us. We also had our own independent study, and then we eventually came up with this GM model.
Is there a resulting paper going to be authored by a faculty faculty and
So it's, we are working on this rural broadband access, where we have participated on the architecture, and that is correct. So the distributed beamforming part is currently being implemented at IIT Delhi. Once that particular, we submitted that paper as a joint paper to IEEE Communications magazine, and it was turned down saying that this distributed beamforming is not implementable. So they wanted to have some proof. So we are currently working on it. Once this is ready, we are going to go ahead. Right now, we do not have. It is a very difficult topic actually. Yeah. So.
Any question from the audience?